this evening, and apologies to Jerry for keeping you waiting, and probably in that process you've changed your presentation completely. But we still hope that you are going to present. So welcome to our second STIAS public lecture for the second semester, and it is the fifth for 2022. We still have one more public lecture to go, and we do welcome the colleagues online. For the colleagues online, my name is Edward, Director STIAS, and my colleague Christoph Poe, the Senior Program Manager, will handle the question and answer session. As usual, we start by making some announcements, and I'm happy that we still have our cohort together. So there are no announcements of people leaving yet. And although the weather hasn't exactly made up its mind, and ESCOM, of course, is doing its thing, I'm sure that we are looking forward to many exciting events ahead of us. The presenters, as I mentioned in the first public lecture, the presenters are presented by colleagues that either have worked with them or have good sense of their work. Eventually, by the time the presenters present, then we get a sense of their work. But we try and get a person to introduce. And for this public lecture, Jerry will be introduced by Professor Thomas Franz. And Thomas wasn't sure that the robots would work, so he decided that he's going to present Jerry online. So welcome, Thomas. And Professor Thomas Franz is Professor of Biomedical Engineering in the Department of Human Biology at the University of Cape Town. His research focuses on biomechanics and mechanobiology from organ to subcellular scale, with application to cardiovascular diseases, cancers, and infectious diseases, and you can see the connection with Jerry's work. The work in cardiovascular disease includes biomaterial and cell therapies for myocardial infarction and heart failure and related cell mechanics in disease. His research group focuses and uses numerical, computational, and experimental methods to probe mechanical properties and behavioral biological structures in health and disease, and to predict effects of therapeutic interventions. He was head of the Division of Biomedical Engineering from 2014 to 2020, and has served as deputy head of the Department of Human Biology since 2019. I should note that Jerry spent a 9-month research visit to UCT Mechanobiology Lab, funded through the Africa Research Excellence Fund fellow last year, and so they worked together with Professor Franz and his team. So we requested Thomas to introduce Jerry. So over to Franz, and I'm sure that I've sort of introduced some of you to some of these terms that Jerry will make it easier for us to understand. Somebody doesn't agree, but we'll see. So over to you, Professor Franz.
Thank you very much, Edward, for the introduction. And thank you for the invitation to introduce Jerry on occasion of this seminar. And I'm going right into it. So Jerry stems from Kenya, and I skipped the very early parts. So Jerry then academically obtained a bachelor and a master's of science in textile engineering from Moi University, where he in the meantime is a senior lecturer. And between obtaining his master's and being senior lecturer, he worked 2 years at the Kenya so now I need to look up. The Kenya Industrial Research and Development Institute. I don't know whether more importantly, evenly important, he obtained a PhD in materials engineering from Ghent University in Belgium in 2017. And then he spent 2 years as a postdoctoral research at the University of Pavia in Italy, all related on computation modeling in the biomedical sphere. Edward, you mentioned or you referred to the African Research Excellence Fund Fellowship that Jerry has received, and in addition to the Alonso Fellowship, which he currently holds with this residency. And I think with that, I will leave it and don't take more time away from Jerry's presentation. And I apologize for not contributing to the explanation of the terms that Jerry will use in his presentation. Thank you very much.
Thank you very much, Tom, for joining. It was nice to see you again after quite a while. Thanks, everyone. Thanks, Professor Edward, Christoph, and all the STIAS management for this opportunity. Allow me to start by thanking STIAS for giving me a chance to take up the ISO-LOMSO Fellowship. The ISO-LOMSO Fellowship has been a pathway for many upcoming scholars in Africa. The impact of this fellowship to scholars and researchers is well documented. Being here to take up this fellowship to me is not just a privilege, but a great honor. So thank you very much. I've been working on a project on computational modeling of tubular fibrous structures for potential cardiovascular applications for quite a while. And in this project, I've mostly been interested in trying to solve problems and limitations of the current technologies of vascular grafts. And when I got the opportunity of taking up the ISO-LOMSO Fellowship, I thought this, like so many other young scholars in Africa, is a great opportunity to try and move the research on cardiovascular structures forward. So here today, I'm going to talk about the ideal graft for potential application in surgery, which is actually the first part of my project and my work. Before developing the computational models, before coming up with the computational models, it's always important to come up with the ideal graft that will be used for vascular applications. But first, I will tell you about cardiovascular diseases. What are they? Their impacts and costs. Why do they matter to us as scholars, and why we care so much to try and study them? I'll then tell you about the vascular grafts, the applications, what are the existing designs, and what are their limitations. What is actually the motivations why we have to try and study these structures. And is there a solution to the limitations of these structures? They'll give you an idea of the ideal vascular graft, the approaches that we use for these designs, and the parameters involved. I'll finish my talk this afternoon by giving some concluding remarks on just why, as scholars, we believe that there is a way of getting an ideal graft, or there's a way of designing an ideal vascular graft. Cardiovascular diseases are actually non-communicable diseases. It means that they are actually not transmitted by pathogens. They will be transmitted by any other means, but not pathogens. Now, these diseases mostly affect arteries and veins by blocking veins, weakening blood vessels, and therefore affecting blood flow. And sometimes they actually cause damage to valves. So cardiovascular diseases, in a way, affect the whole vascular system. What I present here today is actually the basics of what cardiovascular diseases entail. Now, arteries will be carrying blood if they function normally from the heart to the rest of the body. But then cardiovascular diseases will actually affect the whole essence of the blood flow, meaning cardiovascular diseases will actually affect the normal flow of blood in these vessels, and so do veins. Further, these diseases damage organs. In the extreme cases, they actually block blood flow completely. Yeah. Most notable ones are actually the coronary artery diseases, commonly known as the heart attack. Cerebrovascular diseases, known as also as stroke, and also the loss of limb and or their use. So sometimes, due to the blockage of the arteries and veins in the limbs, you might actually completely stop the use of the limbs, or they also lead to loss of the limb completely. But then, how do they come up? How does it happen? So normally, inside the veins, as you see in that illustration, some fats and substances build up inside the veins, such that the flow of blood will actually be blocked or actually be reduced. The substances that build up inside these arteries and veins are called plaques. So when these plaques build up with time, they bring up a condition called atherosclerosis, which is actually simply the plaques building within the inner layer of the arteries. Now this buildup is actually just a buildup of fats, cholesterol, and other substances. So mostly this one affects the carotid arteries, which are the blood supply to the brain, or the blood supply to the heart, the coronary arteries, and also the peripheral arteries, which actually supplies blood to the limbs. So in essence, or in simple terms, blood vessels always get blocked when fats and other substances build up inside them, affecting the flow to the vital organs of the body. And this is the basis of cardiovascular diseases. But then the question is, why does these diseases affect us, or why do we have to care about cardiovascular diseases? And why do we have to care mostly when we live in a continent like Africa? This is the whole essence of my work. I got motivated to start this work when through scholarly literature, I discovered that cardiovascular diseases not only affect humanity, but they more so affect humans in the poorest corners of the universe, as I'm going to tell you in a short while. Non-communicable diseases, of which cardiovascular disease is one of them, kills 71% of people every single year. All the other diseases combined will only translate to 29% of deaths, according to figures from the World Health Organization, the American Heart Foundation, and most scholars. Further, in the developing world alone, all these deaths, 77% of them are in the poorest corners of our planet. 23% is from the developed world. It means that when you live in a continent like ours, you are at higher risk of dying from these diseases compared to those who lived in the developed corners of our planet. And these figures, for your information, they were taken just before COVID-19. So this data doesn't include COVID-19. Of all these figures and data, 17.9 million, are deaths due to cardiovascular diseases, followed by cancer at 9 million, respiratory diseases at 4 million, and diabetes at 1.5 million. It tells you that cardiovascular diseases affects much, much more people than any other non-communicable disease out there. And these are just figures within 1 year. Furthermore, the deaths that are caused or that are due to cardiovascular diseases, 32% of them, they actually account for 32% of all global deaths. In that year, in the year 2019, just before COVID started, 17 million people died below the age of 70. 38% of them were due to cardiovascular diseases. Now, this tells us that the impact of cardiovascular disease can no longer be ignored. And that is why scholars, researchers, and foundations are actually funding the research on these diseases. And that is why most people today are actually trying to understand how to actually come up with ways of solving the problems brought by cardiovascular diseases. What is more is that the rate of cardiovascular diseases is actually increasing, especially in the low and middle income countries. Now, researchers have agreed, most scholars have agreed, that the rate of these diseases will not reduce. In actual sense, one author said that Africa will actually spend tens of billions of dollars in trying to solve the problems of cardiovascular diseases. And that is, as I mentioned, that was way before we started dealing with COVID. Now, on that map, Kenya is actually highlighted. And then on the red pin is Pakistan, and on the blue pin is actually India. Now, Kenya, India, and Pakistan, all of them are actually classified by the World Bank as low middle income countries. In those three countries that I've mentioned, the cost of cardiac care is approximately 434 USD. In Kenya, that will be 52,000, more than 52,000 shillings per person per day. For pediatric cardiology, the cost will be slightly lower at 34,800 per person per day. Now, 52,000 shillings, where I come from, is way beyond the reach of so many. And it tells you why the figures of the World Health Organization and the American Foundation and even the Kenya Cardiovascular Society agree that most people today in the poorest corners of our world are continuing to die because they cannot actually get resources to actually treat some of these diseases. And a majority of the figures that I project here are on the medical procedures, the cost of implants, for example, and equipment. Yeah. When I looked at these figures again and data from the World Bank, I discovered that countries like South Africa are better placed in actually dealing with cardiovascular diseases, simply because they are probably way better than most countries in sub-Saharan Africa. Most scholars agree again that South Africa has a better data on costs, implications, and funding of cardiovascular care or diseases care. And that is why there is actually a big difference between the impact of these diseases in the rest of sub-Saharan Africa compared to South Africa. In one of the scholars actually mentioned that it's only South Africa that has enough data on the impact of cardiovascular diseases. None of any other sub-Saharan African country has enough data on how cardiovascular diseases have actually affected their countries, Kenya included. And that is why on my map, I included Pakistan and India. Pakistan and India are the same level as my country, Kenya. And you can actually, it can actually suggest that the impact on their system and their citizenry will actually be comparable to how we deal with our medical system in Kenya. However, the only difference is that they will import less implants in India and Pakistan than we do in Kenya, for example. So probably in Kenya, that figure, the figure that you see on that slide, will be much, much higher. What I want to tell you here is that the impact of cardiovascular care in Kenya will be much, much higher if I had to report these figures here. But then the question is, how did we get here? We are in a century where technology is very advanced, and we are at a time where we have some of the best facilities for implant production. Is it that there is actually no sufficient implants or treatments for these diseases? The answer is, what exactly do we need to actually treat cardiovascular diseases? And that brings us to vascular grafts. Now, vascular grafts, in simple definition, are actually conduits or narrow tubes that are used to bypass diseased vessels. So when diseases are actually, when vessels are actually diseased or they're actually damaged, we normally use narrow tubes to actually try to bypass them and to actually restore the blood flow to the regions and organs where the blood flow has actually been reduced. We have two types that are relevant to my discussions with you at this afternoon. Those are the autografts and the synthetic grafts. Autografts are grafts that are made from tissues of the same persons, but from different sides of the body. Synthetic grafts are actually the use of synthetic materials to actually create new structures to be used for repair of the diseased vessels. So we can actually use grafts to bypass the damaged vessels, or we can actually use grafts to actually replace these vessels. Now, autografts are the golden method of actually treating these diseases. Why? Because being biological grafts, they will easily fit into the patient and the system and the organs. You don't have to introduce anything foreign to them. So they have actually been preferred mostly for their long-term revascularization of the blocked vessels. And further, scholars have also agreed that they actually assure better survival rates after implantation. And in also the long term, you have lower rates of adverse cardiac events, the recurrence of the cardiovascular events, for example. So this has made them the most preferred way of actually treating vascular diseases. So in essence, autografts will actually be grafts isolated from the patient and then created into grafts and then implanted back into the patient to actually try to repair the damaged tissues. But then what is the problem with them? If we can actually have them and we can actually implant them and there is actually, as suggested here, already protocols on how to implant them into patients, why do we still think they are a problem? Now, the whole essence of actually coming up with autografts or autologous grafts involves invasive harvesting, because you have to harvest tissues and create the graft and actually fabricate the grafts through biological methods as I've demonstrated. But most of the time, the harvested tissues are actually not suitable for developing or for actually repairing these damaged tissues. Sometimes they are actually insufficient in cases whereby a bigger part of the vascular system is actually destroyed. You might not get insufficient donor tissues to actually try to build a sufficient graft. And that is why they are out of reach to many patients, because you're either not having sufficient tissue or they're actually not suitable for the repair procedure. And that is why cardiovascular surgery turned to synthetic vascular grafts. Because the fact that the procedure for actually building biological graft has been complicated by these limitations, scholars have to find a solution, or cardiologists have to find a solution to the repair of the damaged vessels. So the synthetic option became an alternative to the biological grafts. One of the limitations of the biological grafts that I have to mention here is also their costs. Yeah. The fact that the harvesting and production of these grafts are purely biological, their costs are also very high, simply because you cannot also get them off the shelves. So the synthetic grafts have been an alternative for quite a while now. So there are actually two protocols in synthetic grafting. So one is just fabrication of the grafts and then implant them into the patient. But then the problem with the first protocol is that the time for the graft to conform to the host tissues and the adjacent tissue takes a very, very long time. And most of the time, this protocol has not been preferred. The second option has been the the use of cell seeding and cell culture, whereby the graft is actually being fabricated, then cell cultured, and then implanted back into the patient. Now, the second option takes less time for cellularization after implantation. And actually, the conformity of these grafts with the adjacent vessels has been much easier than using the first protocol, as has been shown by many scholars. But what are the existing designs today? There's so many designs that exist from the synthetic grafts. So most of the time, they are just scaffolds or templates which are actually seeded with cells and then implanted. And then, of course, we have the bioreaction to actually induce the cell seeding process. So in one such case, the synthetic grafts have actually been cell cultured, first starting from a porous scaffold, plus this, then cell seeding, and then implanted into the patients. And another option which exists on the right-hand side of that slide is actually where the cells and the scaffold are actually being fabricated into a mold. And both of them have actually been tested. Yeah, these ones have actually gone past clinical trials. Now, in this approach, the findings were that the strength of actually these scaffolds are very, very encouraging. Yeah. Now, the whole idea of actually the synthetic grafts is actually making them as close as possible to the biological graft or to the autografts. The closer they are in properties to the autografts, the better they will behave after implantation. And that is why you will actually see the component of cell seeding in actually most of them. Another approach was actually now trying to change the graft, the vascular graft template a bit by actually now reducing the pores and also again using the mold. But then now you actually discovered that the mold, so here scholars are just trying to change either the template, the original template, or the way the cell seeding is done. So in this one again, the clinical trials were very positive, and they were actually being able to be implanted in patients. Another approach actually involved the using of both animal and human donors, whereby the cells were actually harvested from animals and then isolated and then seeded into the grafts. And then that was actually compared by cells from humans seeded again into the templates or the grafts and actually and then implanted into patients again. Here, the major finding was that even though there was actually better strength, the graft didn't actually behave well in grafts that were less than 6 millimeters diameter. Now, apart from those, there have also been grafts that have been fabricated from electrospinning. Electrospinning has been one of the major production systems for vascular grafting. And in one such case, a vascular graft has been produced by trying to have both random fibers on the outer side and aligned fibers in the inner. And then again, seeding cells at the interface or in the inner sections of the graft. Now, this approach actually ensured a very strong product. The approach ensured that the strength or the mechanical strength of these grafts was actually very improved. In another approach, on the right-hand side of that slide, you actually see now a triple layer. In the first one, there was a double layer, and then the second one, then there was actually a triple layer. Now, what scholars or what researchers are trying to do is they are trying to improve here the strength of these grafts, to actually try to make them more strong, but also they are also trying to make them to withstand a lot of pressures in the vascular system. Remember, during blood flow, there's a lot of pressure that these structures have to withstand, and that is why the different approaches are trying to improve on their strength. But then, what is the problem with these ones? Apparently, as I've demonstrated, there have been so many approaches, and so many of them, as you've seen, that are trying to actually build structures to ensure that they look more like the natural vessels. But then they themselves are not perfect. They still have limitations. The approaches that you've seen here of the synthetic grafts, they don't behave well in small vessels, especially vessels that are less than 6 millimeters, which are actually most of the vessels in the human body. The patency rates will go to as low as 32% after 2 years. So it will start from 60% after 1 year, and then in 2 years, it will be actually at 32%. So it means that the time from when the implantation is done to when an intervention is required, it normally reduces much more after the second year. They have also suffered from the inability to withstand high pressures, especially in the arteries. The blood flow in the body is under a lot of pressure, and some of these grafts have not been able to withstand that pressure, again, in the long term. Something that I also want to mention to you is that the reason that the biological grafts have done so well is simply because they can survive for a very long time before an intervention is required. Yeah. In some documentation, it's been reported that they can actually survive for 10 years before any intervention is required. Now, the synthetic grafts, on the other hand, will not have such an advantage. They will actually collapse, or they will actually require, let me use the word require intervention before, for example, 10 years. So, apart from that, again, the issue of them not being strong enough to withstand pressure or have enough strength to withstand the mechanical pressures. So apart from that, they've also been prevalent failure rates. These grafts have been failing for so long. The efficiency, therefore, is very low, and there's actually a high rate of blockages due to blood clots. So these attributes, and many others, have actually ensured that synthetic grafts have not been adapted seamlessly in cardiovascular surgery. There's actually a problem when it comes to how these grafts have to be adapted. Most clinical trials have actually highlighted that these grafts are still very far from actually replacing the conventional vascular grafts out there, especially the biological vascular grafts. Another question is then, is there hope? Can we actually still get the ideal vascular graft that can improve on the limitations of not just the biological graft, but also the synthetic grafts? Because remember, scholars, surgeons, and most of the researchers out there have looked at how to improve on vascular grafts, first from the biological grafts and to the synthetic grafts. But then at that level still, we still have a case whereby we cannot adapt the artificial grafts for cardiovascular surgery. And that's what brings us to the idea of the ideal approach of fabricating an ideal vascular graft. There is actually hope that an ideal graft can still be fabricated, and there's actually hope that with more research we can develop a graft that has the ideal attributes of a graft that can behave much closer to the biological grafts. Electrospinning is actually a process where vascular grafts have been fabricated, and it's actually the most realistic approach for fabricating vascular grafts. Electrospun grafts have shown that they can actually be able to mimic the native cells and the adjacent vessels. Therefore, if you look at the way they behave in these grafts, they compare much better in terms of compliance matching to the biological grafts. They have improved properties, for example, and much better tissue regeneration compared to actually the synthetic grafts. You can actually say that their properties are much closer to the autografts than what the synthetic grafts are. The whole science of electrospinning is actually trying or spinning solution into fibers and then forming cylindrical tubes. But then now from randomly placed fibers, as demonstrated on the right-hand side of that slide. So here we are using high voltage sources to actually get fibers from solutions. So the solution there would actually be a material, a biodegradable material, which is actually spun to produce nanofibers, which are actually formulated into a tube. So these structures, or the structures from this system, they are the closest way or the closest approach to actually getting the ideal graft. But then electrospun graft themselves still needs to be optimized. The fibers in electrospun grafts are randomly placed, and the system itself, the production system, involves a lot of parameters. The voltage sources, the viscosity of the solution, for example, the speeds of the spinning, for example, the size and diameter of the products. So we still need to optimize the system so that we have a vascular graft that will give us better outcome during implantation. And some of the parameters that scholars agree that will make better or will make their structure better are actually mechanical properties and their porosity. Now, porosity here is just formulated by looking at the openings or the spaces between the fibers. What you see here is actually an electroscopic image of how the internal structure of these grafts will look like. So in this sketch, you actually see that in the microscopic structure, the fibers are actually aligned randomly. And not only that, there is actually spaces between them. Now, during their use, the cells actually get to be implanted or get to be seated within those spaces. Now, the more you have the spaces, the more cells you actually get during seeding. Now, if you can actually optimize not only the size of the spaces, but their distribution within the structure, you are able to get a structure that can have optimal properties. Not only that, remember these are fibers in their nanoscale. As you can see from the scale at the bottom of that slide. So we are talking about nanofibers, fibers that are less than 10 nanometers, for example. Now, the only challenge that have always been there during the production of these structures is how to get a uniform distribution of these fibers. Remember, if you can get a uniform distribution, then you can actually predict their strength and their performance eventually. So in the ideal approach, we're actually trying to come up or to actually design uniform fiber diameter. Uniform fiber diameter because we want to see if the fiber distribution diameter is uniform, can they have uniform, for example, cell attachments? Can we have uniform strength, for example? And one of the approach that we use in this design is Python programming. Python programming, as I'm going to demonstrate shortly, is a programming language that has been used for parametric modeling to try and create structures from their microscopic level. So one approach here is actually to use numeric Python. Numerical Python, or NumPy, is just a set of libraries for scientific computing. Here we want to build the fibers from their base units or from the individual fiber units. We also want to get the fiber dimensions using mathematical transformation and actually construct the wholes of the graft from the fiber level. And the fiber level here referring to the nanostructure. So this approach includes defining the fiber number, the total fiber number. So all the fibers within the structure are given a parameter, a number T, for example. And then the fiber diameter, how thick or thin these fibers are. And then the orientation. The orientation here is actually how one fiber crosses the other. Then if you look at the bigger structure, then now you get the graft diameter, its radius, for example, which is half of the diameter, and also its length. So numerical Python includes coming up with a program, as demonstrated there, whereby we start with defining the dimensions, for example, and then the coordinates. But then something very interesting is that you can actually build the structure either from straight lines or from Bezier splines. Both of them will actually be applicable. So all the fibers you see in the structure on the right-hand side can actually be built either by starting from a line, a simple line, or by starting from Bezier spline. So this is what I mean by a Bezier spline and a line. So defining the start point and the end point of your Bezier spline, you can actually be able to get the starting point of your line. Or you can actually simply use a line segment and then apply a random command to actually multiply the lines for as many as you want. So both using the Bezier spline approach or the line segment approach have been realistic in building these structures. So how do we do it? So the first step is actually just starting by a line, defining its coordinates from where it began to where it ends, for example. And then using, again, a random command in the second step to get a planar network of the fibers. And then using a cylindrical transformation to actually build the structure. So you can actually change the dimensions to get any formulation that you want. Now, what is so special about this design is that the fibers are actually built from the base point and into their thousands to actually come up with this structure. We can actually be able to predict where each fiber is inside the structure, either starting from a line or from a busy spline. Now, in this approach, we're actually trying to generate fibers. And not just that, we're actually trying to generate them and actually place them at every point inside the graft. So the first design here is actually just trying to come up with a fiber network and then replicate them so many times until you actually get a planar network and then roll it into the graft. Now, something that's also very special about this approach is that all the line segments, wherever they are placed inside the structure, you can actually determine how much spaces, for example, you really want to see, or what is actually the density of holes or spaces within the fibers. Something that's very crucial, and as I demonstrated in the synthetic grafts, the most realistic way of implanting these grafts is ensuring that they are cell-seeded before the implantation. Now, the more the holes that you have inside your graft, the more the cells you'll be able to implant inside them. Now, this approach gives us an opportunity of determining how many of the pores or the holes we will be having inside the graft. And then the second step is, in the analysis, we'll actually simply trying to mesh the fiber or to generate the meshes. This is just in a way of trying to see how the performance of the graft will be. And of course, we do deformation of the structure as well, trying to see how strong it is, trying to see how the fluids flow will actually happen inside this. And of course, we have post-processing where we're actually trying to optimize. Remember I told you as I was starting that optimization of these structures is actually what we are required to do. And therefore, in our approach here, we're also looking forward to actually optimize them by actually looking at how they are performing in the long run, especially using virtual simulations. So one of the properties that we wish to optimize is actually the actual bending. During the implantation, they're actually not implanted in a straight profile. They actually take the profile of the vessels that they're actually connecting. And therefore, analyzing their bending potential will be important in knowing how they will behave during or after implantation. And we do that by using the crimping mechanism. The crimping mechanism is actually a mechanism of trying to force the structure to actually bend several times and actually see how the stresses and the strains in the structure will actually behave. Eventually, we will actually be loading these structures. One of the weaknesses of the vascular grafts has been their strength. The failure rates of these grafts has been well documented. And therefore, looking at how they will behave mechanically by actually trying to load them in their uniaxial axis will actually be important. But not only the tensile loading, we'll also be looking at the cyclic loading of these structures. And it will also be important to look at the stress distribution, for example. What will be the stresses and the strains in these structures? Remember, for them to actually pass as vascular grafts, they must be able to withstand the stresses and the strains of the vascular system. And getting some of those parameters inside these structures will be crucial. And this is one of the approaches that we entail to use to actually build these structures. Test virtually these structures. So you can actually load these structures by using displacement-induced loading, but you can actually also use force-induced loading, whereby you start your loading using now forces instead of just displacing one part of the structure. And this one will actually give us also an idea of how much forces they will actually need before they deform. Eventually, the internal pressure. Internal pressure is actually the pressure of actually how these structures will behave when they are actually forced by forces from the internal part. And this one can actually be simulated by actually applying pressure in the internal walls. So these are just the properties, just some of the properties that we entail to actually use to actually study this ideal vascular grafts. Remember, even though we entail or we have created the ideal vascular grafts, for them to actually be able to be used or to be actually considered as vascular grafts, they must have specific parameters and mechanical properties like the biological vascular grafts. This is just some of the properties that we entail to look at. Finally, the concept of designing an ideal vascular grafts is actually the most realistic chance of fabricating a vascular graft that can look like the natural vascular graft. This idea is actually our best option in trying to reduce the limitations of finding an efficient and cost-effective structure to actually be used as a vascular graft and a candidate for synthetic grafts. The Python language approach that I've demonstrated here today is the most realistic potential, the most realistic, and has the potential of actually producing a vessel that can actually spur the innovations of not just fabrication, but clinical trials to better fibrous structures for cardiovascular applications. Thank you.
Well, Jerry, thank you so much for gently guiding us in your talk from a very general to a very technical level, and for helping us understand, as Edward anticipated, a lot more about this amazing work that you're doing. Congratulations. So we'd like to open the floor for discussions, comments, questions. I've noted several persons online, so welcome to all of you who have joined us online. You're welcome to use the raise hand function if you're online. We will see it on the screen here, and then we'll be able to give you a chance to speak to us. In fact, we'll be able to see you on the screen, so please feel encouraged to switch on your camera when you would like to raise any questions or comments. So let's take any questions, comments from the floor for a start. I saw Simon Becker's hand. Please use the microphone for the sake of our online.
May I first say, Jerry, that I think the presentation was extraordinarily intelligible to scholars like ourselves. Many of us are not in the same discipline as you are, and I mean, I would really like to congratulate you in your presentation to scholars. I have two questions. The first question is, as one of the scholars outside of the natural sciences, I would have thought that there is the issue of when one takes a vessel from outside a human body and then grafts it onto vessels within a human body, that the graft itself, where the internal vessel meets the external vessel, needs to be able to implanting, in other words, needs to balance itself in some chemical sense. I mean, there needs to be some form of chemical marriage, if I may put it that way, at the point of the graft. And if you could speak a little about that in general, but also in terms of your approach, how that chemical chemical marriage takes place. I mean, that's my first question, which is hopefully intelligible, making sense. My second is more general. My second is, I have a book here by Charles Tilley, who is a philosopher, historian, sociologist, and the title is Why. And what he does in the book toward the end of his life is he tries to explain how explanations take place. So my question to you is, having really communicated very well with us, the scholars sitting here, if you were to have 3 or 4 or 5 patients who don't have the backgrounds we have, how would you communicate, through what kind of story, without using the technical language, how would you communicate to them what it is that you are trying to do? Or or do you think it's important to be able to develop some kind of story for them, which would not include all of the technology? Thank you.
Thank you, Simon, for your questions. Your first question was about the chemical conformity after implantations. Remember, I've mentioned here that for the sake of the scope of my work, I've only concentrated on the autografts and the synthetic grafts. I've ignored the xenografts, which come from different species, and the allografts, which come from different people, from one person and then implanted into another. The reason why I intentionally did that is because for us to actually move to the complexities of different species and how these grafts will behave in another species, we have first to actually see if we can get an ideal parameter, right? We can actually get ideal parameters for a vascular graft. As I've mentioned in my discussions here today, is that the limitations of the biological grafts, which are simply easy to implant, or the golden methods that have been used for implantation, the limitations are much more, and still scholars are trying to solve these limitations. The synthetic grafts that are actually developed to actually replace them still have a lot of drawbacks. And therefore, if you look at how the xenografts, which are from different species, and the allografts, and then you'll discover that it's way more complicated, and that is why I intentionally didn't want to talk about them here. As you mentioned, definitely the chemical reactions will not be perfect. Scholars have actually reported of cases whereby these structures are rejected by the recipients, for example. Yeah, so it's still a subject that many scholars are investigating on how to reduce the rejection rate, for example, and that is why I didn't want to discuss them with you here today. On your second question, how to communicate what I'm doing to non-scholars and patients. What I'm doing here is just trying to come up with solutions to problems of cardiovascular diseases, which as I've shown you, have causes deaths to so many people in the developing world. It's clear that the burden of cardiovascular diseases is real, way before COVID. And coming up with solutions, coming up with ways of making treatment cheaper, coming up with ways of making the processes more efficient is what my work is all about. Thank you.
Thank you, Simon. So I saw 3 further hands, Carlos, Hendrik, was it Brian and then Alison? Would you be happy taking 2 questions at a time? Okay, Jerry. So Carlos, please go ahead. Oh, yes.
Very nice. Oh, sorry. Very nice, Jerry. My question is much less philosophical. I was wondering, how do you arrive from the computer design to the physical entity, the actual graft, and whether some kind of a 3D printing technology is being used to making the actual graft?
Thank you, Jerry, for, as Christoph put it, gently guiding us through the basics to where you ended up. And Carlos just stole my question, so I won't repeat it.
That's fine. So Jerry, please go ahead. Thank you very much, Carlos and Professor Hendrik. Have I fabricated real grafts? Yes, I have. Professor Thomas Franz mentioned that I spent some time in Cape Town, at the University of Cape Town, on my last postdoc fellowship, working on the development of electrospan vascular grafts. So I started from actually making the real grafts. I have done this for the better part of the year 2021, and I've studied their mechanical properties in real life. But as I've mentioned, as I was having this discussion with you, is that the problem we have with them is that because the fibers are random, we cannot actually predict the fiber thickness, for example, and the number of holes that we have in these structures. It makes their performance still below par. And that is why I thought that can we make a virtual graft and see that we can predict not only the placement of these fibers, but the eventual performance. Now, if we can come up with this option, we can actually see if we can go back to the lab again and create this theoretical graft that I'm demonstrating here today. Thank you.
Thank you. Right at the back, and then Alison.
Thanks, Jerry. Yeah, Carlos also stole my question, but I have others. The first I'd like is a question of clarification. So when you're talking about seeding these grafts with cells, presumably the cells are from the donor patient. Would be okay. So then, how long does that process take? Because so very often, when you're having a heart attack. It's, you know, the intervention has to be really rapid, and you know the process of seeding and doing all of that kind of stuff presumably, I would imagine takes days, if not weeks.
Thank you, Brian, for your question. How long does seeding take? It takes quite a while, for sure, unfortunately. But then. This is why this is why researchers are working on this. We want eventually to make these grafts be available off the shelf. That's actually the long-term goal of this research. That if you can go to your doctor, you can be able to get the grafts simply off the shelf. So seeding is actually part of the process of making them, but eventually they will be available. They should be available, so to speak. So you will not have to wait for them to be made. You'll actually have them during surgery. Yeah. And this has been done for sure. Most of the scholars that I've quoted in my presentation today have actually tried to make some of them available off the shelves. Yeah. Of course, they have the limitations that I've mentioned, but they are eventually available. Thank you.
Thank you. And Alison.
Yes.
I always thought that cardiovascular disease was a disease found more in the wealthier countries, from too rich foods and things of that nature.
So I was surprised that it's so prevalent in poorer countries, and in Africa. How do you explain that?
Thank you, Alison. The fact, the notion that cardiovascular diseases was the disease of the rich is just a misconception. What I didn't tell you today is that scientists are struggling, for example, to explain how the plaques that are found in the inner lining of the arteries, when do they start? Some of them say they start from birth, for example. And two, cardiovascular diseases come from inactivity, for example, less exercises, wrong diet, smoking, for example, and so many bad habits. And these two are found in the developing nations, not just in the developed world. So when people used to believe that these diseases are prevalent in the rich nations, or they are diseases that only affect you when you are born in a well-off background, for example. But information that we have from scholars and data out there suggests this is not necessarily the truth. Cardiovascular diseases affect everybody in every part of our society today.
Thank you, Alison. Carlos has a comment.
Just a quick comment on Alison's question. In Jerry's slide, you look, for example, at the US, it was listed as a rich country. If you go there, I mean, there are poor people in the US, right? And these diseases impact those much more than the people that are well off. So if you go even inside the same, so it's not rich country versus poor country, it's also within country. Yeah.
Jerry, we have two comments on the chat, so I presume the expectation was that we'd read them to you. So I'm going to read you two of them. Okay, so you can respond as you see fit. First, from Joshua Kubi, he asked, please mention something about interaction of endothelial cells with the synthetic fibers, especially with deposition of lipids and aging. How does this affect stiffness matrix? Can I read you the second question, or would you like to respond to that first?
The interaction of endothelial cells and their
with the synthetic fibers?
With the synthetic fibers.
Yes.
Now, the cells during cell seeding, or after culturing and then during seeding. After culturing and during seeding, we have ways of actually inducing the migration and eventually growth of these cells inside the structure. So they will not only migrate into the structure, but we have for example, in one of my slides, I mentioned the bioreactor. So the bioreactor is actually where the conditions of how these cells migrate into the structure and the way they populate into the structure and the way they get attached inside the pores happen. So inside the bioreactor, we have not only the conditions, but also the necessary chemicals where these cells attach themselves to the synthetic structure. But how do they affect the mechanical property of the structure? We want eventually that our artificial graft to behave like the biological graft. Now, in some cases, the synthetic graft after cell seeding have actually been removed, so that the structure which have the cells have been left inside the vessels after implantation. In other cases, where the synthetic material is biodegradable, the cell and the structure have been molded in a way that they still behave like the adjacent cells. One thing about these structures, or one thing about them, is that we are looking at the way to improve their conformity, the way they'll behave with the cells they're attached to, with the vessels they're attached to, and all the adjacent vessels. And that is something that we are still working on. Can we make their conformity better after cell seeding, for example, than they are now? Thanks.
Okay, thank you, and thanks for that question. And then one other question from Praise Matsekete. Also thanks you for the presentation and wants to ask, when it comes to optimizing for parameters, how does the model account for material properties? So is there a specific set material that is used for vascular grafts, or is there some variation in the options available in the market?
Thank you. During optimization, we simply assign the material properties of the fibers themselves. So the fact that we are actually building these structures from the fiber level, we assign to the fibers the material properties of their biodegradable materials in the market. For example, if our structure is made of polyurethane, for example, we'll assign it material properties of a polyurethane, and we'll actually simulate the behavior of these structures as a polyurethane structure. So during our optimization protocols, we want to look at their performance. Their performance means we want to bring them as close as possible, for example, to the parameters of an autograph, for example. So we want to optimize them such that the performance of these structures and the performance of the biological grafts are very, very close. And we do this by trying to ensure that we not only give them the material properties of the synthetic grafts from the nanofiber level, but we also simulate the performance also in that regard. Thanks.
Yes.
It's incredible to me that you can operate so at the nexus of so many disciplines. You have to really understand so many. So you obviously work with teams, and you work. I'm curious about two things. How do you work in the interdisciplinary team? Like, Jerry, I'd just like to hear you talk about that experience. And then can I ask you a really unfair question? And the question is, do you think with this kind of incredible advances that we have in computational modeling, that we can move away from medical experimentation on animals in the future? Perhaps. Is there a hope and a possibility of that?
Thank you, Sandra, for your question. The first question is, how do I work in multidisciplinary fields like this? I found myself in this by chance. My background is in engineering. I had to take a PhD in biomedical engineering, working in an orthopedic lab, trying to develop structures for repair of flexor tendons. And it was simply applying the engineering base principles to solve medical problems. The engineering principles are well developed, but they have a cross-cutting. They actually cross-cut into the medical field. When you flex your fingers, for example, these are simply mechanical movements. The finger flexes and extends. Now, if you look at that from the engineering point of view, you discover that you can actually look at forces, you can actually look at movement, you can actually look at displacements. So what I bring to the bioengineering or the biomedical field is the principles of how mechanics works, the biomechanics, so to speak. Trying to understand what surgery needs from an engineering perspective by trying to actually apply engineering knowledge. So it's simply applying mathematics, engineering, and science in trying to solve some of these problems. And as I can tell you, the medical field needs a lot of engineering applications. They need a lot of engineers to actually operate some of their machineries and actually also design some of their implants. The whole essence of design is engineering and science, but they're actually applied by some of these cardiologists and surgeons. So that is actually how I found myself here. That was way back in 2013 when I started my PhD. I evolved further and I discovered that there's so much that we can share across fields, and that is what actually makes sense in research. And two, most of the funding agencies today would want you to apply your knowledge across fields in trying to help society. I've just mentioned to you that I was born in Kenya. I was surprised that Kenya is a low-income country, while South Africa is almost a first world. I just learned that the other day. But what I wanted to say is that the problems that society suffers in a country such as mine needs re-engineering of our solutions. We cannot rely on doctors alone to actually come up with solutions to the medical problems. We cannot rely on politicians alone to come up with solutions to the economic problems. We need an interdisciplinary way of looking at life. And I've found a lot of relevance in this way. To your second question, with the development of computational modeling, can we do away with animal trials? As we heard from Carlos on Tuesday. The answer is no, we cannot, unfortunately. Clinical trials will still go on animals. Before we implant these structures into human beings, they must go for clinical trials, and this will start from animals. Computational modeling would be looked at as the base or as the fundamental step towards clinical trials. Once we actually develop the ideal graft, can we now try them on some of these species, and then later on upscale it to human for human application? So even though we have advanced in computational modeling, even though today at my fingertips I can do my programming at the comfort of my house, we still need clinical trials in animals. Definitely, yes. Definitely, there will be much fewer. And there are some things that we were trying clinically in the 80s that we might avoid now because of some of these advances. I agree. Thank you.
Thanks, Jerry. Thank you, Sandra. We have one more question. Yes?
That was my contribution was going to be that before we need to use the animals, we'll be more sure. It doesn't occur so quickly.
Okay, well, Jerry, thank you so much. Thank you for all those wonderful questions and inputs, and also from the online audience, thank you for attending. We really look forward to seeing how your work develops and evolves over the years to come. We're privileged to be associated with your work for the Isolomso Fellowship, the duration of that, and one day we'll buy these veins off the shelf and we'll think of Jerry. Thank you.